So welcome to another video on gPROMS. So in this video, we want to solve a simple reactor problem. So we have just one equation here, and we are going to perform a sensitivity analysis on the rate constant. Okay, so let's get started. Now, what do we do first? We open a new gPROMS project. So file, new, then you have a new project. So remember, you need to identify the parameters and the variable in the model. So in this model, you can see that volume is a parameter, is known. We have the value for volume. So we have concentration is a variable. So that is what we are tracking over time. So that's the dependent variable. Then we have the feed rate as 175. So that's a parameter. We have the flow rate Q as 1 meter cube per minute. And we have the rate constant K as 0.15 meter cube per grams per minute. So you also have the initial condition. So at time t equals 0, then the concentration in the reactor of the reactant is 0. So you have to solve the ODE for 30 minutes. So now we have just one variable, and we have like 5 parameters or 4 parameters that we need to declare. Okay, so we need it to first create a variable type because the concentration. So let's create a variable type called concentration. So you have concentration so edit the concentration. I can put the units of concentration here is in grams per meter cubed. I can put plain text, grams per meter cubed. Then I can put upper bound of, let's say, 100,000 and lower bound of 0, and keep the default value as it is. So I have the variable type. So now if I create a model, so on the model, right click, new entity. So you can close that and close this one. Right click, new entity. If I call it the mixed reactor, just call it mixed reactor. And I have the model created. So if I go to the gPROMS tab, so I'll delete the templates. So I need parameter. So what are the parameters I need? I need volume. So I need volume as real. I need, what else do I need? I need the feed rate. I need the feed rate as real. And I also need the volumetric flow rate. Volumetric flow. Remember, you cannot have space in between. For parameter name, you cannot have space there. So that's why I'm using the underscore as real. Then we also need the reaction rate constant. Trying to be descriptive here as real. Okay, so I think that's all I have. I need. Then variable. So the only variable that I have here is concentration. The concentration as so that's the variable type concentration. Now equation. So I have the equation I have is V, which is volume multiplied by time derivative of concentration, which is $sign concentration equals F, which is the feed rate. F is the feed rate, you see in the problem. Then that's minus Q is the volumetric flow rate. Volumetric flow volumetric flow. Then that's volumetric flow multiplied by concentration. So I can go to, so I can continue writing the equation here. Multiplied by concentration minus K, which is the rate constant, multiplied by, so I can make this bigger. So okay, I'll come back to the equation. So multiply by, so the equation multiplied by V, then C squared. Okay, so by V, which is volume, times C's concentration raised to the power 2. Okay, so that's the equation that we have. So what else do? We create the process to solve the model. I call it simulate mixed reactor. Then I can, the first thing to do is to define the unit. So I call my model reactor here as mixed reactor. So this is the name I want to use in the process as the name of the model. So basically I'm creating a copy of that model. I'm renaming it as that. Then I have some parameters to set. So set, so I can do within reactor, do. So because I don't have access to those parameters directly, I have to find a way to go inside our model. So that's what I'm trying to do there. I can also do reactor dot, then the parameter name, then set the parameter name. So what are the parameter names that I have? So I have volume. So if I put them to here, I have volume colon equals. So I have feed rate not equals. I have volumetric flow rate not equals. I also have rate constant not equals. Okay. So what are the values? So I have volume is 12, constant feed rate is 175. So let me put them side by side now. The volume is 12. So volume is 12 meter cubed. That's meter cubed. Then feed rate is 175 of the unit, grams per minute. Then volumetric flow rate is 1, which is meter cubed per minute. And the rate constant is 0.15. 15 meter cubed per grams per minute. Okay, so now I have set the parameters. So this initialization procedure that is appearing here, if I want, I can deactivate that. So if I come to entity, I can uncheck this. So if I click on that, I want to remove it, so it's gone. So what did I? No, did I check something else? This should go. Okay, I'm not sure why. That is still there. Okay, so you can leave that one. Unexpected input. So if I put schedule here, that should go away. Unexpected input. Okay, yeah, that should be there. Yes, I want to save the model now. So I'll save it in document and just call it batch. Save. Okay, so it's gone. So maybe if I try to remove that now, yeah, it's gone. Okay, so I have set the parameter, then all I need, because the degrees of freedom is 0, I have one variable and I have one equation. I need initial condition. So under initial, I need to specify the initial condition, C, on the concentration at time t equals 0. So concentration, so I will do reactor dot concentration equals 0. Remember, initial conditions are equations, so not assignment. Then, what do? I solve it. So, all I need to do is continue for 30 minutes. So 30. Okay, make it bigger. If I run it now, in plotting interval of 1, then I should have the results. Result trajectory, reactor, variable, concentration, and there you go. So that's the concentration over time. Okay, so now the second part of the problem says perform a sensitivity analysis. So I want to see how the concentration responds to change in the rate constant. So if I change the rate constant, how does the concentration change? So to do this, there are different ways to do this. One way is to create like 5 copies of this reactor. So I will just create reactor 1 as this, reactor 2 as that, reactor 3, and within each of that, then set the new values of the rate constant. So for example, if I say, okay, reactor 1 as that, then I can just say, create another copy, reactor 2, create another copy, reactor 3. So I'll do that. So, and then within this reactor 1, I set the value of the rate constant. So I will increase this by 0.05. So this becomes 0.2. Then the initial condition, within that reactor, I will set that as well. Reactor 1, initial condition, and I will run it. I will do the same thing for reactor 2, but this will be too long. So there's a compact way of doing this. So the compact way of doing this is to define how many times you want to run the simulation for. So how many iterations you want to do. So like you want to change the K values 5 times. So that means we can define a parameter like an iterator, and then we create an array of reactors. So we create an array of reactors, which instead of creating one instance of the reactor, we create an array of reactors, 5 reactors, for example, and then loop through each of the reactor and assign in a smart way, change the value of K. So let's see how we can do that. So now the first thing to do is to create a parameter. So I don't want to do this long way. So I don't want to use a long way. So parameter, then I call it iterations. So this will be an integer. So like 5, for example. Then this under unit, instead of creating reactor as mixed reactor, I create reactor as array of reactor. How many? Depends on iteration. So array, depending on how many iterations I have. So it's going to create that copies of reactor. If I have 5 iterations, there'll be 5 reactor in that array, in the list, basically, of mixed reactor. So this is how we create the array. As an array, then you put of the model that you're using. Then I set the value of the value for iterations. So I will do iterations column equals 5. I want to do it 5 times. Remember, I didn't do reactor dot here. Why? Because iterations is declared within the process. Okay, so I declare that within the process because I don't need it anywhere else. Then I loop through this array of reactor. So to do that, I'll use for loop for I colon equals 1, 2, number of iterations I have. So what do I want to do? I want to set the value of k. So that's all I want to do. So within the, so if I do I there, so within I, when I is 1, it's going to go inside the first reactor. So reactor, then it's going to be 1, reactor 1, do, what do I want to do? Change the value of the k. So how do I do this? There should be a way of doing this. The smart way of doing that is to link I value, link this I to the rate constant. So if I do, remember it was 0.15 before. So when I is 1, I want to leave it at 0.15. So if I do, well, the step is 0.05. So if I do 0.05 times I minus 1, then plus. So what this will do is that when I is 1, so this is 0, so that means nothing will be added to this. When I is 1, when I is 2 rather, so this becomes, everything here becomes 1 times that, then that will be added, that becomes 0.02. When I is 3, so 3 minus 1 is 2, 2 times that is 0, that's 0.1, and that becomes 0.25 and so on. So it's going to continue until I is 5. Okay, so when I is 5, this becomes 4 times that gives 0.2, and we add that to that, that gives 0.35, which is where we want to get to, okay? So that's a smart way of doing it. So once you do that, then we can do the initial as well. Loop through it for I colon equals 1 to iterations do. Then what do I want to do? I want to set the value of the initial condition for each of them. So end, always end do. So end within and end the for loop, rather. Always end for loop. So this end, we end within. And this end, we end for loop. So here, this end ends for loop. Okay. So what will happen here is reactor 1 dot the concentration equals 0, reactor 2 dot, reactor 3 dot, and so on. Okay. I think that's all you need to do. Then if you run it, it's going to create arrays of reactors, 5 reactors basically. So if I run, then I should have, so this is the old result, this is a new result, trajectory reactor. Now you can see that I have 5 reactors, and within each, I can expand. I'll have the variable, okay? Graph, that's it. Then to see the effect, it's better to send this result to our gRMS. So the plotting tool in gPROMS. So I'm going to make a new video to explain how to use gRMS, but let's send the result to gRMS to see how it's going to look when we plot. That will allow us to put all the results together, all the concentration profiles together. So to do that, I will check the send results trajectory to gRMS. If I click on that, it's going to open gRMS, so which is the plotting tool. So it's open there. If I expand that, if I click 2D, then add line, so which is that red line there. Then expand that. So this is the first reactor, the concentration, okay. Then expand the second reactor, the concentration, okay. Expand the third reactor, concentration, okay. Then the fourth reactor, then the fifth reactor. Okay. So then we can look at the profile together. You can see how K affects. So as you increase the value of K, then what happens? Then the concentration, the final concentration drops. Okay, so for the first reactor where K is the lowest, you can see the value of C, the exit concentration is the highest. Okay, so that's it for this video, and I will see you in the next video.